amplifier. Okay, so using an NMOS. Okay, so typically we had NMOS, which we had called M1. Okay, whose source grounded the gate to which we were applying the input. Okay, across a drain we used to take the output. This is my drain, and then we add a load resistance. And I said the disadvantage of having a passive resistor, okay, is it occupies more area on an IC. Okay, and because it's all about the small scale transistor integration, so it is not predominant to have the passive resistor. So instead of going with the passive, we would have gone with the active device there. So that's why we used three input PMOS, where gate and drain shorted, it becomes a diode kind of connection as an load. Okay, so we are replacing a passive load with the active load. Okay, so and that was possible. Okay, with this is gate, this is source, and this is drain of my PMOS, which I had called as M2, and where gate is shorted with the drain. Okay, and the source of this PMOS was going to the VDD. Okay, this is what, and we were ensured that M2 should operate in saturation region. Okay, so this is what our requirement was. Okay, and in order to have this, or to operate this M2 PMOS in a saturation region, we should ensure that the VDS is very much less than the VGS minus of VTP. Okay, so it's a magnitude that we had taken. Yeah, so the moment we ensure this M2 in saturation region means the current flowing through this transistor, which is now acting as a diode or a load, will be constant. Okay, so in saturation region, the current is basically a constant. And this is what we had said. So if we add a resistance of some 100 ohm, VDD is fixed and the resistance is fixed, means there is a constant current flowing. Okay, in the similar fashion, we are replacing a resistance, which is a passive component, with a active device with the two terminal diode kind of connection of this transistor, ensuring it to be operating in saturation region, making sure my current is constant. So now this is just acting as a constant current source, a constant current source. Typically it is now acting as a load. Okay, this is what we have. And for an amplification to happen, okay, so using a transistor, we should ensure that this particular M1 should be in the active region. Okay, this should be in the active region. M1 active region, M2 saturation, saturation constant current, and active region, it is in this. Okay, and also we ensured that whatever the current that is flowing through this, the current through M2, I call it as ID2, and it is a constant. Okay, and since my M1 is also 1, and the current that is flowing through this M1 is ID1, so we can say that ID2 is equal to ID1, or ID1 is equal to ID2. Okay, so this is what the things. With this, then we are taken the gain expression for NMOS. So we are interested in the gain of M1 transistor. Okay, because this is the active transistor that we are using as a for an amplification. Okay, so A1, which is for M1 transistor, I'll tell you, for M1 is given by GM times RD I had taken. Okay, and with minus sign, just to indicate that output with respect to input, whatever the input I give in terms of sign, and the output is also signed, but there is a 180-degree phase shift. Okay, so negative is basically a phase shift. Okay, for example, if my input is my VGS here, if my input is this, my current is the output. Okay, it will be going in terms of this. You can see that when the input is positive, output is negative, and when the input is negative, output is positive. Okay, so this is my output, and as this is my input. Okay, so output is current, input is voltage, so that's why it is the transconductance that is coming into picture. RD is this, and finally, and since it is the M1 transistor gain, I call it as something like GM1, and RD is basically a load resistance. Now load resistance is replaced by M2 now. Okay, so that's why approximately my RD is equal to 1 over GM2. Why GM2? Because it is the M2 transconductance. Okay, it is GM2. So this is AV1, which is nothing but what? Minus GM1 by minus of GM1 by GM2. I just put a bracket here. Okay. It is not that GM1 is minus, it is the gain that is minus. Okay. And then the GM, that is the gain. Okay. So as we have seen in the previous session, okay, what is the gain was given by? It was given by, okay, that is the transconductance of transistors. Okay, so GM1 is twice, since it is an NMOS transistor transconductance, it is mu n, okay, offset capacitance into the width by length ratio of this into the ID1. This is the GM1 divided by, correspondingly we have GM2 as 2 mu p Cox W by L of M2 into ID2. Okay, so this is what we have. And we know that mu n is approximately 2 to 3 times of mu p, but we are taking mu n to be equal to twice the mu p. You can take 2, 2.5 or 3. Okay, so based on this you can see what is the gain that you are finally getting at the output. Okay, so this is what we are, and this is what we are considering. This is one we have. Okay, this is one, this is the another one. Okay, so now I'll just replace wherever mu p is there with the mu n is there with the mu p. So my AV1 becomes minus of a root. I'll take this entire root common now. It is 2 times so of 2 mu p Cox W by L of 1 ID1 divided by 2 mu p Cox W by L ID2. This is of 2. This 2, mu p cancels, Cox. ID1 and ID2 gets cancelled because both are equal now. So I'm left with AV1 equals minus of square root of 2 times W by L1 divided by W by L of 2. This is what the expression finally I get. Okay. So now designing, okay, since we have to now choose W by L of NMOS and PMOS, and before that we have to ensure for what particular gain we are designing this common source amplifier. Okay, and that is what we are trying to see now. Okay, so we had AV1 as basically now minus of root twice W by L of 1 divided by W by L of 2. So now I will design this common source amplifier for gain of 10. Okay, this is what I have to design. But still there are the width and the length ratio of are unknown. So what I'll try to do is I'll try to choose the NMOS transistor width and length. Okay, so width of NMOS I will keep it as something like 5, and the length I'll choose it as something like 1. This is what is my W by L ratio. Okay, this is equal. Okay, so now substituting this in the above expression, I get 10 is equal to minus square. I will take this side, so this becomes 10 square. Okay, the square root I'll be taking towards left. It becomes this. It is W by L is 5 by 1 of this divided by W by L of 2. Minus, we are not interested because it is with respect to the phase shift between the input and output. Okay, so now the W by L of 2 is equal to 5 by 100. Okay, so 10 square is 100. So what is this? 5 ones are 20, or it is 2 by 20. So how much you will get? So what is W by 2 now? Yes. Yes, what is the W by 2? Fast.
Sir, numerator on 2 ಇರ್ಬೇಕಲ್ವಾ?
Numerator ಅಲ್ಲಿ
2.
Yes.
Factor 2.
Yeah, okay. Good. So this is into 2. Okay, I forgotten to write there. So now what it is now? Yes,
1 by 10.
it is 1 by 10, but make sure here one important aspect here. The width of PMOS, okay, minimum should be, I'll repeat, the width of PMOS, okay, minimum should be 2. Okay, I can't have the width to be something like 1 that I've got here. So how to make this as something like 2 now? The width should be 2. Yeah,
2 by 20.
it's 2 by 20. Okay, it is 2 by 20. Is that clear now? Why we are ensuring, even though it is 1 by 10, we are ensuring that since the minimum width, PMOS minimum width should be 2, okay, we are ensuring that this is the width that is has to be 2. Okay, length we are not worried, but we are worried about the width, so that's why we are ensuring. So even though we are getting this 1 by 10, but the minimum width of the PMOS should be 2, so we are having 2 of width, and length correspondingly will be 20. Okay, so if you substitute this W by L of 2 and W by L of W by L of 1 in that above AV1 expression, again you will get the gain to be something like that. Okay, so hope this is fine till this point. This is what we had done in the last class. Now we'll try to uh, draw the schematic, and we'll try to simulate and get the AC analysis, DC analysis first, from where we get the biasing point, and then we find the transient analysis, where we'll try to see if input is some value, what is the output, whether we are getting the amplified version, and finally we are going with the AC analysis. Hope everyone is fine till this point. Fast.
Yes, sir.
Yeah. Okay. So
Yes, sir.
yeah. Who is this? Who is this? Akhil. Yeah, you are absent. Yeah. So, no, you are absent. Okay. In the sense that you didn't listen. Okay. Akhil? Okay. Anyhow, true, right? Akhil. Come on, see. Which is the active device that we are using as transistor? NMOS. Is PMOS acting as a transistor here, or it is a load kind of thing? Load. Yeah, that's why we are not worried about the PMOS characteristics with respect to width and the length here. Is that clear now? And this is what I think the Geeta Patel asked at the end. Okay, so I had asked any clarification. She had asked, what is this? Why the width and the length ratio of PMOS is the ulta? Okay, something like this. So clarified there. Since M2, that is the PMOS, which is now acting as a load. Okay, instead of passive resistor, we are ensuring that this is acting as a constant current source. So that's why we are not worried about the width and the length, but we are worried about only the width. Minimum this particular software requires, or the design requires, is 2. Is that okay? Yes, okay. Hope this is fine now. Yeah, that's why. But if you see the NMOS, the active device which is acting as a transistor, that's width is greater than the length. Okay, so this is what we are. And now going to this electric tool. Okay, so everyone knows how to use this. So that's why. So I have a PMOS on top, NMOS at the bottom. Okay, you can see that the transistor properties of NMOS. Width is 5 as we had designed, and the length is 1. Okay, and then this PMOS transistor, width is 2 and length is 10. Okay, still if someone asks me again why I can divide this, since it is a ratio of W by L, it becomes 1 by 10, but width of PMOS minimum should be 2, so that's why we are retaining the width and correspondingly the length value. Okay, so this is what we have. And make sure that you have this P-SPICE model for PMOS and NMOS. Okay, and Vin is my input, VDD is my power, Vout is my output, and VSS is my ground. And again, you have to make use of 4 terminals transistors here, devices. Okay, so the 4th terminal of that is the body of PMOS, and don't neglect that. Okay, so it is now not the transistors, it is acting as a load, so we can neglect this 4th terminal. No, you should do the procedure as it is that clear, everyone? The body should be connected to VDD, that is PMOS, and NMOS body should be connected to VSS. Hope this is fine. Yes, don't neglect this 4th terminal, and this gate is connected to the drain of PMOS, which is basically a drain of NMOS and PMOS shorted, and this is where we are taking. Hope this is fine. Yeah. Okay. So this structure is now similar to this now. Okay. Where W by L, so M2 W by L is 2 by 20. Okay, whereas M1 W by L is 5 by 1. This is what we are taken, and that is what we are ensuring here. Okay, so this is what we are. And if you see this structure, okay, whatever this figure is all about, okay, this is similar to this now. Okay, and make sure that now first analysis, when we are starting to do all this, the schematic is done, the piece-wise model for NMOS PMOS is defined. Okay, then the corresponding pins directions has been defined and all, and even specify the width and length ratios of PMOS and NMOS according to the design. Okay, so the very first analysis that we are going to do, okay, is the DC analysis. Okay, this is very important. Okay, so DC analysis is with respect to the output plus input. Okay, so I vary the input in terms of DC from 0 to maximum. Okay, so I'll be checking how exactly it will be done. Okay, so the DC analysis typical characteristics. Okay, this is my V out and this is my VN. VN I vary. If this is 0 volts, if this is 5 volts, in a steps of 0.1 or 0.2, it will be simple linear going. Okay, so the output accordingly, I'll have some transition, something like this. And wherever this two curves intersect, okay, this is what my DC operating point. Okay, operating point, or we call this as something like biasing voltage. And this biasing voltage is very important for us. Okay, so the SPICE model for DC analysis is, you'll include all those things, dot include dot electric, wherever the C5 models are there. Okay, so the P-SPICE model, it is VDD is with respect to VDD and the ground. Yes, so this is what the typical thing you write, VDD to references ground, and DC we are specifying something like 5. Similarly, VSS to ground reference, DC it is 0. Then the Vin is Vin with respect to the ground reference. Okay, DC again 5, and then since it is a DC analysis dot DC, It is the V in that I am varying from 0 to 5, and this with the steps of 0.1. Okay, so this is what my DC analysis will be there, and here you will include wherever that C drive, all those things will be there. Okay, so electric and so on and so forth will be there. Okay. So now we just try to have this yeah, so this is what we have dot include. Okay, all this thing VSS V in we are okay, so V in is 0 to DC. Okay, so DC analysis means it is all with respect to DC. Okay, that is all about VDD, VSS, VN, and then it is the DC analysis dot DC. VN we are varying from 0 to 5, the steps of 0.1. Okay, this is what. Say okay. Yes. So save. Okay. So tool, spice tech, write this. Yes. Okay. You can see this spice amplifier thing. So now add variables. It is V in and V out. Okay. And you can see this is what we are getting. Okay. So this is the blue line corresponds to my input. Okay. And this green is my output. Okay. And you can see there is an intersection happening. So typically the inverter you had seen the transient analysis. Similarly here also, but you can see that even though VDD is from 0 to 5, you can see that the output is not having a transition from 5 somewhere at the 2.5 something. Okay, so this is an amplifier now. Okay, we'll see what exactly the output will happen now. Okay, this is the operating point. Okay, you bring the bars here and you can check, or I can directly go and intersect here, and correspondingly you can see here the moment this cursor goes here, you can see the y directions will be varying. Okay, so you can see that. Okay, the y bottom, you can see that x-axis and y-axis points it is giving. So y is because we are interested in the y aspect. Okay, what is that output value of thing we are having? So it is 8 point. So the intersecting point now is basically 0.820 volts. Okay, this is what we are having. This is very important now. So that's what we are trying to write here. So intersecting point, that is the operating point, is 0.820 volts. So typically I can approximately 0.8 volts is the operating point, DC operating point. Okay, so the DC operating point is 0.8 volts. So this is one important aspect that you have to first find out, the DC. Yes, so you can see that intersection y-axis 0.8. Don't go beyond that 0.82. Take it the lower side value, that is 0.8. Okay, so this is what the DC is all about. Yes. Next, once the DC is done, we have to do the transient analysis. Okay, so transient analysis is with respect to input and output. Input is the amplification input that we are giving in terms of AC. Okay, so that's what we try to do now. Okay, so VDD, VSS is same. Now only thing that we have to do is, now instead of V in varying this, so we have to change these things now. Okay, so V in is V in reference 0. It is the sign we are giving. It is not the pulse now. It is the sine wave, because small signal model, right? Yes. So input is the sign I am giving. I am not giving the pulse, sign. Okay. Now very interesting aspect. The first field in this particular V in. Okay. I'm giving something like 0.8. Can anyone tell me what is this 0.8 corresponds to now? 0.8 voltage, sorry. What is this 0.8 corresponds to?
So DC operating point.
DC, this is DC operating point, okay. So why this 0.8? That is the DC operating point, okay. Ensure that this is the DC operating point of mine, okay. Then input, okay, it's a sine. What is the peak? So I am just putting something like this now. 0.005, that is one peak. It is not peak to peak, okay, it is one peak. 0.005 volts is my input signal amplitude, peak amplitude, not the peak to peak. And then it has a frequency of 1K, okay, that is the one clock cycle. That's what I mean by, okay. So all are small in case, SIN sine. 0.8 is the DC operating point, 0.005 is the peak value of input sine signal with the frequency of 1K. And then there are three parameters which are not interested, that is with respect to phase Gs and all. I am not worried about that, and I will have something like 50 samples, okay. The last value, that is 50 in this parenthesis item, is 50 cycles we'll have, okay. So that is one. And then we'll try to do the transient analysis. Dot tran is from 0 to 5 millisecond, okay. So this is what will be my transient analysis now. Just say okay. You can see that it changes. Once again I repeat, the VDD and VSS is defined. So previously Vin was DC because we are doing the DC analysis. Now it is the transient analysis. What is the input that I am giving? Input is the sine, and that is what I am defining. Vin the input with the reference 0, it is a sine. 0.8 is the DC operating point. So now you can see that my sine, okay, is added on top of my DC. Is that clear? The DC operating point is the DC value. This AC is added on top of my DC, okay? And because of this sine wave, that is the AC signal, we are getting the amplification version. Okay? So save it, okay. Again, go for simulation spice with the right spice deck. Save. Yes, you can go. Yeah, I can just now go in with visible trace, V in and V out. Yeah. So can you see this input signal and the output? The top is the output, whereas the bottom is the input. Suppose if you want one more, I can go for add trace. I can just take this. That's it. Okay. Yes, this is still better. I can say. So you can see that input is varying in terms of millivolts. Okay, if you see the y-axis, I mean x-axis is with respect to time. Okay, transient analysis. You can see that input is varying in terms of milli because I had given the same thing. Okay, so from where to where it is there. Okay. And output is with respect to my volts. Yes. Is this okay? Is this okay? Fast.
Yes, sir.
Yeah. So now
Yes, sir.
you have to find the peak to peak now. Okay. So what is the input peak to peak? Because we want V out by V in. That is what my gain is all about, right? So gain. Okay. So now the gain is basically V out by V in, and that is what we calculated in the previous session also. Okay. And what is the peak to peak input and what is the peak to peak output? That's what. Okay. If I just go with this is my bottom of the peak, you can see y is somewhere around y value is 1.04 something. Y value is 1.04. This is with respect to my V out calculation. Okay. And the top peaks is somewhere 1.12 or something. 1.12. This is the minimum and this is the maximum thing is 1.12. Okay, this is what I am, and that's what I've written. So y max is 1.04. This is 1.12. And similarly, I can just go with this input. Okay, it is 795 milli. Okay, so I can go with V in as 725 milli. Okay, and this peak is somewhere around. Okay, I mean 8.4. So Y minimum and Y maximum as 80. Since we know what is the input, okay. If I now have the difference, okay, so we have difference. So I have 1.12 minus of 1.04, which is basically 0.08, or almost I'll be getting V out to be 0.08, and this is point divided by 0.01. So it is 0.1 I get approximately. Okay, so if I just go with this, okay, I just want to remember here. Okay, so this is what. So you can see this difference of this and this is your V out. Almost I am getting 0.1 difference. Okay, 0.9 or 0.1 difference. Here it will be 0.01 difference because I'm having 0.005 as the input. So the peak to peak becomes 0.01. So finally, I have something like this. The V out is 0.1 divided by V in is 0.01. Okay. If I just do that, 0.1 divided by 0.01, so it is approximately almost 10. Okay. If you go with specific, if it is 0.9, okay, 0.09 divided by 0.01, it is approximately 9 I am getting. Okay. So we are designed gain for 10, but we are getting gain to be 9 approximately. So, but we wanted the gain to be 10. Okay, so how to get still more near to the theoretical value of the designed value gain? Yes, anyone? How to get this now? Yeah. Yeah, it's all about the mobility. A mobility of electrons we have assumed twice the mobility of holes. You can change. You can now keep 2.5. Okay, and you can alter and see in for what particular exact value of mu-n ratio with respect to mu p you will get the exact. But still, sometimes you may get 12 as a gain. If you have designed for 10, you might get 10. I mean 12. Now we are getting somewhere around 8 or 9. Okay. Is that clear? Yes. Hope this is fine. First, DC analysis, get the operating point. Next, you go with the transient analysis, ensuring your V input to your amplifier is a sine. And the very first value in this sine is the DC operating point. This is very important. Okay. Make sure that your operating point is same. Suppose if I just change this, I'll just close this one. Okay. Okay, so I'll just make it is something like 0.82. Okay, I'll just even you can vary this also and check. Okay, save. Okay, issue. Okay, I can just use it twice. V out. You can just see now what really happens. Okay. So I will go with something like bottom is 860 milli. Okay, I have 860 milli with respect to V out. I'm saying 860 milli, and this is now 950. Okay, again I have some difference of 90 milli. Okay, and here any of the input doesn't change, but still I'm just we can check with respect to input also. So now I'm getting 0.09 by 0.01, which is again 90 something. Okay, so it is still going in a better way now. Okay, so we had 8 What was the value of this? 8.829, right? Okay, just a minute. We'll check what was this. 0.820 here. Okay, no issues. Okay, so you can just try to change this. Yeah. So DC analysis is done. Transient analysis done. From the transient analysis, you can get the measure of gain. What exactly? Okay. And finally, now after we have this, finally we will be going for the AC analysis. Okay. So VDD and VS remain same. One change is there from the transient to this. Okay. So Vin is still the sign, but here we have to specify it is an AC signal. Okay. That is the only one change that you will be seeing in the AC analysis. Okay. Keep it transient analysis. This AC factor doesn't come into picture. Whereas this in the AC analysis it comes, it is dot AC. Okay. Now in the transient analysis, your x-axis was time. Now in the AC analysis, what is your x-axis? Fast. What is your x-axis of in AC analysis? Fast. Yeah. Fast. Anyone? Come on. It is in terms of frequency. Okay, so this is what we are trying to plot, the gain versus the frequency. Okay, this is the other way of finding out your gain, right? Yes, plotting. So this is in terms of frequency, and we are ensuring that that it will be in terms of decade. The frequency x-axis, which is frequency, it will be varying in terms of the decade plot. Okay, we start from 100 hertz. Okay, with the step of 100 till 10 giga. So giga G is in the capital. Oh, this is fine. The AC analysis. Two changes from the transient analysis. One, the input V in, no doubt it is sine, but between 0 and sine, you have to put something called AC. Okay, because it's an AC signal. And rest all remains same. The fields within the parenthesis remain same. And the AC analysis dot AC, and this frequency, which is the x-axis, where it is varying in terms of decade. Okay, so it's a decade frequency axis. The initial frequency is 100 hertz. It varies with respect to 100, the steps, and this is till 10 giga. Okay, so this is what we save it. Okay, tools, simulation spec, write specs, spec. See, okay. Here, add visible trace. Check. Go with the. Okay. And this is what your AC analysis is about. This is your view. Now, hope this is fine. Y-axis we have taken in terms of frequency, that too in the decade. It is not a linear graph. Okay. Similar to your transient analysis, this is a decade plot, and I'm varying in terms of 100. Okay, 100 hertz, 1K, then 10K, 100K, 1 mega, 10 mega, 100 mega, so till 10 gain. And then again, you can get your gain. Okay, so you have to come 3 dB below. Okay, you can see where is your operating frequency and the corresponding gain in dB, and finally you can convert that gain into the normal gain. Okay, so this is how you have to. You can just even check the gain aspect in your AC analysis also. Okay, but in order to do AC or transient analysis, this is very important. Okay, this field is very important for me. Okay, because that is nothing but what the DC operating point. Yeah, hope this is fine. Anyone is having any clarification? Fast. Of the common source design, starting with the gain expression. Finally, designing for gain of some value. Even if you don't want that gain to be 10, okay, we can just change my gain to be 20. We'll see what really happens now. Okay, so gain I want somewhere 20. Just change this. Yeah. So now I want to design for gain of 20. Yes. So again, I'll go with W by L of NMOS to be 5 by 1, which is predominantly 5. Okay. Then AB is 20. So mu n with respect to mu p is twice the mu p. Still, I'm retaining the same. So mu n is approximately equals to 2 mu p. You can change. Okay. So when you're designing, don't use twice mu p. You can use 2.5 times mu p, and you can vary and see. Okay, whether there is any change that is happening with respect to gain. Yes. So if you want a whatever the designed gain, if you want exactly the same thing, you can just vary this mu n with respect to mu p and you can get it. This is what I have. So finally, what we'll have? So gain is 20. 20 square is equal to twice of 5 divided by what is 20 square by W by L of 2. Yes. Now W by L of 2 is equal to 2 into 5 divided by what is 20 square? Yeah.
Sir, 400.
Sure, huh?
Yes, sir. Yes, sir.
No, okay, 400. 5 ones are 5 8s are 40 na. Fast.
Yes, sir.
So my W by L of the PMOS, is it 2 by 80? Is it 2 by 80?
2 by 160.
2 by 160 na. Henge. 2 by 160 yakappa. It is, if not, it is. Yeah, 2 by 160 hengagutte. Is it okay? 2 by 80? Yeah. Fast. 2 by 80 na 2 by 160 na.
Sir, yes, sir. 2 by 80.
Okay. So now what I'll try to do is I'll just change this, the PMOS. Okay. So 2 by 80. That's it. That's what we'll try. Okay. So I'm doing the DC analysis, right? So for DC, V in to reference 0, DC C5 dot DC V in 0 to 5 steps of 1. This is what I have. And anyway, NMOS is not changing now. Save it. Tools. And steps. Visible trace. V in, V out. Okay. You can see this 0.766, right? I can just have so DC operating point. Okay. DC operating point is 0.75. I'll just go with this approximately. Okay. This is what I have, 76 or 75 because it's okay. So now we'll just go with the transient analysis. V in. So what should be your transient analysis now? V in 0. It's a sign. Okay. Parenthesis 0.75. Okay. Input is still I retain the same thing. See, input you give as minimum as possible. Okay. Don't give in terms of 1 million. Is that okay? You just give small because We want to see the amplification here, right? Yes. Don't give the magnitude. You just give the small signal so that it should be amplified in terms of 10 times, 20 times, 30 times. Okay. So that's very crucial now. It's a 0, 0, 0. 3 field has to be 0. I want samples. Done. Okay. Dot RAM. 0. Oh, save. Yes. Okay. Please. Okay, you can just go and check. So that's fine. Input is 0.7446, 0.756. Almost point. Not one is there. Not one is there. Okay. Try to see what exactly this is. 0.91. Almost 1. So 0.911. So it is 1 milli. So I'm just getting something like 10. Okay. You can just vary your mu n and mu p now. So now the gain, because this difference is 0.915. This is 1.05. So 0.91 and 1 is almost 0.01 I'm getting. So 0.01 and 0.01 and 0.01. So it is somewhere around 10. Still I'm getting the same 10 gain I'm getting. Okay. So you can just vary this mu n and mu p and you can see what really happens there. Okay. So this is what. Keep changing the parameters mu n and mu p, and also with respect to the operating point. Okay, I've used 0.75. It was 0.766. You can even still keep 0.766 and see. Okay, so 2 parameters you can vary. Exactly, you can give the operating point whatever you have got, and just vary the mu n and mu p, and mu n with respect to mu p, 2 or 2.5 or 3 or 2.2 whatever. Okay, and just plot. So design aspect. The analysis, first starting with DC, then the transient, then the AC analysis. Transient is with respect to output versus input, and your AC is with respect to output versus the frequency. Okay, where you will get the graph plot, and you can find out from that AC analysis also what is your gain that you are getting. Yeah. Hope this is fine. Any clarification doubts in designing this common source amplifier, and also the schematic drawing, what all the piece-wise model has to be done, and how exactly your width and length ratio of PMOS and NMOS has to be initiated. Yes? Any clarification? Fast. Yes, no? Is common source amplifier design and the simulation is clear? Yeah? Okay, so this is what, in this week, this is what you will try to do. Okay? So, don't come and try during the lab session itself. Whenever you are free, okay, you just make everything, do one set of analysis before you come. The moment when you come to the lab, you can just tell us that what you have done, what is that variation you have done, how to get the exact near to the design value of gain. Okay, what all needs to be done. Okay, you just get some inference there and you can share it to your friends along with me. Is that clear? Yeah? All of you?
Yes, sir.
Yeah, so this is what you have to do. Okay, so I think I'll stop here. Yeah, so tomorrow onwards I'll go with the regular classes. This was the instruction that was to be given, and next I think we can go with the common drain amplifier maybe in the next instruction class also. But this week, this is what you have to do. Yes. Yes, Anubhav.
Yes, sir.
Yeah, if no more doubts or clarification, I think we'll stop here.